So, good afternoon, everyone. Sorry for the technical problem that we have. As usual, we kind of when I'm in place, I always have technical problems. So this was not a new thing or wonder that this happened. So I do apologize, Sarah, for everything. So welcome, everyone. My name is Violeta Vasilevska, and me and David Dean, we are welcome to Math Week on behalf of the Math Week Committee. Today, we welcome our keynote speaker, Sara Del Valle, and she will be talking about real-time data fusion to guide disease forecasting models. Something about Sara, she's a scientist and a deputy group leader for the Information Systems and Modeling Group at Los Alamos National Laboratory. As a scientist, she leads an interdisciplinary team focused on detecting, understanding, and forecasting infectious diseases using heterogeneous data streams and mathematical, computational, and statistical models. Most recently, her team has been investigating the role of large-scale data analytics, such as satellite imagery, internet data, and climate, and complementing traditional approaches to inform infectious diseases, disease modeling, and political instability. Her work has been covered in several top media outlets, such as National Geographic, NPR Science Friday, Popular Mechanics, and the New York Times. Sara received a PhD in Applied Mathematics and Computational Science from the University of Iowa. She also has a Master and Bachelor in Applied Mathematics from the New Jersey Institute of Technology. Please welcome Sara Del Valle in her talk, Real-Time Data Fusion to Guide Disease Forecasting Models. Thank you, Sara.
Thank you, and I also apologize for all the technical difficulties. Violeta, do you want me to just kind of shorten my talk and then, or how did you want to do this?
So we are recording, Sara, so just go on.
Okay, great. So I'm going to start. I did have some short clips in my presentation, and so I'm going to try to see if when I use my microphone, you can still hear the audio, because there's audio on some of my slides. So we'll see how that works, and let me know if you can't hear well. I'll try to see what I can do. Anyway, okay. So I kind of first wanted to start with my journey before I go into my technical presentation, just to give you a brief overview of how I ended up here and how I became a scientist. I was born in Mexico. I moved to the U.S. when I was 16, and after I finished my high school, I joined the New Jersey Institute of Technology, and I got a bachelor's and master's in applied mathematics. And I always loved mathematics, and I always thought I was going to become a math professor, because that's what I thought mathematicians did. However, while I was an undergraduate, I went to Cornell University for an REU program, which is a research experience for undergraduate program. And this is, I feel like this was a critical piece in my journey because I became interested, and because I was introduced to mathematical epidemiology, and that really changed basically the course of my journey. I learned during this summer program how I could actually tie mathematics and epidemics and study infectious diseases. And so after this program, I decided to get a PhD, and so I went to the University of Iowa to get a PhD in applied mathematics and computational sciences. And while I was a graduate student at the University of Iowa working on my PhD, I was given the opportunity to come to Los Alamos and and do a summer internship, basically. And after I came here, I never left. I just completed my PhD here, And for those of you who don't know what Los Alamos National Lab is basically a government research institution that performs a lot of different research. It was originally founded to work on nuclear weapons and the nuclear bombs that were dropped in Hiroshima and Nagasaki. But after the 1940s and 1950s, the research portfolio expanded, and now there's a lot of different research that is being performed here. From climate change to infectious diseases and materials and many other different types of research. And so now I work here at Los Alamos, and I've been able to actually utilize my expertise in mathematics and apply it to the study of infectious diseases. And so I'm going to play a clip, and let's see if the sound works. But this is from National Geographic. They featured our work a few years ago, and so they really kind of capture the work that I do here. And so I'm going to try to play it. And so I'm going to put my microphone here and see if this works. And nowadays, infectious diseases are a national security issue.
Sara Del Valle is part of the first line of defense against what could be the next global pandemic.
You can clearly see how it starts at airports, Chicago, Atlanta.
At Los Alamos, they run what-if computer simulations to predict how far and fast the fallout from a biological weapon might spread and how many people might die.
We need to figure out how to quickly distribute vaccines and treatments. After the anthrax release in 2001, there was a concern that other diseases could potentially be spread, and so that's why we started developing these systems that could allow us to understand what-if scenarios.
What-if scenarios can be terrifying and fun.
I hope you were able to hear some of the audio.
So Sarah, can we ask David? David, was the audio okay? Oops. David, okay. Are you able to see everything?
The audio was good.
Okay. Sorry. Go on, Sarah. Just checking.
Okay, no, that's perfect. Given all the different connectivities that we have, it's better to check. And so now that you kind of understand what we're doing here, we have a team that works on using mathematical and computational models to understand infectious diseases. And I always like to start with our overarching goal, just so that people can see what we're trying to do with all this modeling. And so basically, we want to improve decision support by understanding and forecasting disease outbreaks, and we're using a lot of different data streams, a lot of different models, and I'll go into a little bit more detail about some of the models that we're using, and also quantifying model uncertainty, because as you know, there's a lot of uncertainty in some of the data and the models that we're using. And we are borrowing a lot of the approaches from the weather forecasting community, and I like to kind of start with this because it's easier for people to understand. We've been using weather forecasting for a long time, and so it's easier to see how we are translating what the weather forecasting community has been using for hurricane and just weather forecasting in general. So basically, what they do is they take observations from many different sensors. They have satellites, they have ground sensors, they have sensors that are deployed in the ocean, and then they take all the data from all these different sensors and then combine them with models to provide forecasts with cones of uncertainty. And so you've seen, how they're able to update their forecast based on new data. And this is the approach that we're taking for infectious disease modeling. And so basically, we are also trying to exploit different types of data from social media, news sources, obviously clinical surveillance data, and we're combining them with mathematical and statistical models, and then we're providing probabilistic forecasts with quantified uncertainty. And this is the link to our COVID-19 forecast, which is covid-19.bscgateway.org. And so you can kind of see how we're also trying to project where the number of cases for COVID are going to be going, which is very similar to what you see for hurricane forecasting. And so this is kind of like the overarching goal of our team and our project. And so now I'm going to start go into a little bit more detail about how we're using mathematical models for infectious diseases. And I wanted to start with a little bit of history about epidemic modeling. And the reason why I wanted to start with a little bit of history is because I think you're probably seeing a lot of modeling now for COVID-19, and it's very good that now a lot more people are familiar with how mathematics are actually being used to understand infectious diseases, but this is actually not new. We have been using modeling to understand epidemics for a long, long time. And these are just a few examples of how people in the 1600s, in the 1700s, etc., use models to understand different infectious diseases. And so I wanted to highlight in 1855, John Snow did a very interesting analysis for cholera. So basically, a lot of people were coming down with cholera, and people didn't really know what was the cause of cholera. Basically, they didn't really know that water is how cholera is transmitted. So what he did is he took a map of London, and because he had the addresses of all the people that had been infected with cholera, he mapped those people onto his map, and he was able to find that most of all the people that had been infected with cholera were around a water pump in the middle of London. And he realized that the one thing that all of these individuals shared was the water, this water pump that was actually causing cholera. And so he used a very simplistic spatial kind of analysis to understand to identify the source of infection. And obviously that now there's a lot more sophisticated spatial analysis to understand how diseases spread and everything. But this is just to kind of give you a little bit more information about how things began, basically. And obviously there's a lot more, in understanding typhoid and, Sir Ross in 1911, he actually won the Nobel Prize for using models to understand malaria, and he was the one who was able to identify that mosquitoes were the source of infection for malaria. Anyway, so now going forward to 1927, Kermack and McKendrick were the first ones to actually provide the foundation of what we now use for infectious diseases or communicable diseases, and this is the model that they proposed. Basically, it's a very simple model, but it's very powerful and has been used in many different occasions to understand the spread of diseases, and currently many groups are using these SIR type models to understand COVID-19. And basically, you have three different compartments. You have a susceptible, infectious, and recovered compartment, and you can describe this with a system of differential equations. And then the rate at which a susceptible person gets infected is by this rate lambda, and then the rate at which a person infected recovers is at this rate delta. And then you can see that this is a nonlinear system because you have the susceptible person has to have contact with an infected person, and so you have the nonlinear components there in the DSBT class. And then if we just know something about the number of contacts that people have, the transmission of the disease, then we can actually describe how disease is spread. And then one particular measurement and piece of information that is very important for infectious diseases is the reproduction number. And I'll go into a little bit more detail later, but basically this metric has been very powerful in helping us understand how diseases is spread. And I think it's just it's interesting that such a simple model can actually have, can describe basically how diseases is spread. And then if you basically know the values for some of these parameters, for the C, for the beta, for delta, then and then you plug it into your model, then you're able to basically describe an epidemic, and you have the infected class basically going up and down as you've seen for COVID-19, the susceptible population decreasing, and then the recovered population increasing. And this is a very simple model, but obviously you can add a lot more compartments depending on the disease that you want to describe, and you can add a death compartment or an exposed compartment or any other different compartments to basically describe a more complex system. And so I wanted to just also highlight the reflection number, because this is such an important piece of epidemic modeling, and basically the magnitude of R naught or R0 basically determines the severity of the pandemic or an epidemic or an outbreak. And if R naught is less than 1, basically, if you cannot infect, if on average people don't infect more than one person, then the epidemic will die. But if people infect more than 1 or 2 or 3, then you can have exponential increase and then have a lot of disease spread. I also wanted to give you some homework, and this is if you haven't watched the movie Contagion, I highly recommend it. It's a great movie and interesting to kind of see some of the things that they played out in the movie Contagion actually happening in real life. And I just wanted to also show you a very short clip from this movie about R naught, and I was just really fascinated that Hollywood was actually able to capture some of the mathematical terminology and jargon that we use into the movie. So let me play this short clip.
Biggest shopping event of the year. I think we need to consider school stuff. And especially with kids, people that work in stores, government workers, people that work in hospitals. When will we know what this is? What causes it? What cures it? Things to keep people calm. Once we need to determine that for every person who got sick, how many other people are they likely to infect? So for seasonal flu, that's usually about 1. Smallpox, on the other hand, is over 3. Now, before we had a vaccine, polio spread at a rate between 4 and 6. Now, call that number the R naught. R stands for the reproductive rate of the virus.
Any ideas what that might be for this?
How fast it multiplies depends on a variety of factors. The incubation period, how long a person is contagious. Sometimes people can be contagious without even having symptoms. We need to know that too. And we need to know how big the population of people susceptible to the virus might be. So far, that appears to be everyone's hands, the mouth, and the nose. Once we know the R naught, we'll be able to get a handle on the scale of the epidemic.
So basically here, it's interesting to kind of see how the R naught was introduced into a movie. So that was kind of interesting. And so as is described here, basically the R naught, and it's a product of a lot of different things. You have to take into consideration the susceptible population, which is described here as of 0. Delta is for how long someone is infectious, and obviously the transmission of the virus and number of contacts. And if you include mitigation strategies, you can also capture how those mitigation strategies can potentially impact the reproduction number. And so, okay, let me try to look at the next. And obviously, as I mentioned earlier, you can make a lot more complicated models depending on what you're interested in. If you need to account for age structure, then you can break it up in, by different age groups. If you want to capture other complexities such as different towns or different schools all connected, then you can basically describe it with a system of differential equations. However, the lambda has become a little bit more complicated because now you cannot just be infected by people in your class or in your community, but you can also be infected by people in other classes or communities. And so now moving on to, that was just kind of the introduction to epidemic modeling. And so now I wanted to talk about how we're using all these different tools to basically forecast flu in real time. And before I go into into more detail about how we're doing that, I just wanted to provide a few definitions because sometimes I use forecasts and sometimes I use projections. And so forecasts basically attempt to predict what will happen based on trends, and this is a lot what you see for the financial industry or for some of COVID-19 forecasts and also hurricane forecasts. But also we have projections, which are the projections attempt to describe what would happen given certain hypotheses or what-if scenarios. And so the most of the SIR type models are projections because you have to make assumptions or basically play with what-if scenarios, what happens if I reduce my number of contacts by half, or what happens if I get vaccinated. And so all of that is what-if scenarios, and they're different than the forecast. And so I'll try to stay consistent with my terminology, but this is just something for you to keep in mind, especially because there's been a lot of forecasts and projections for COVID-19. So we started working on forecasting around 2013, and basically the CDC started a flu forecasting challenge, and so they wanted to see how the flu was spreading across the U.S. And basically the structure of the challenge is as follows. The challenge starts in October and it runs through mid-May. And every Friday they release data on influenza-like illness, which is what you're trying to reproduce. And then you have to provide forecasts the following Monday. And the CDC is basically interested in 7 different targets. So they're interested in the week when the flu season will peak and how intense that will be. So basically what percentage of the population are going to be reporting influenza-like illness. They also want to know the week when influenza will pass this threshold that they have set for the nation, and basically want to know when things are going to start to increase and get bad. And then they also want 4-week ahead intensities. And so basically, if you are providing forecasts on Monday, they want to know how many people will be reporting influenza-like illness in the next 4 weeks, basically. And so the first thing we did basically was to try to fit an SIR model. And here on the top, I'm showing you the fit of our best SIR model to flu season in 2011, 2012, 2013, and then 2014. And you can see that, the SIR model is able to sort of capture the structure of the epidemic. It goes up and down, and you can basically describe the epidemic with an SIR type model. However, you can see that there's some things that the model is actually not able to capture. One is these peaks that you're seeing, and because the CDC is interested in forecasting when the flu season is going to peak, the SIO model is not really able to capture that, and so you can see that in many of all of the systems that I'm showing here, we don't really capture that. And another thing that we noticed is that week 14 is always higher than week 15. Basically, you can see a dot on the week 14 and then a blue dot for week 15. And so there are certain complexities or structure that are happening during the flu season, but our model is not really able to capture it. And so, in order for us to basically capture the flu season and forecast the flu season, we decided to add in additional pieces to our model. So basically, we have an SIR type model, but then we decided to add two pieces, which are common discrepancy and then the week-to-week discrepancy, basically. And when we combine the SIR and the discrepancy terms, then we're able to actually replicate the influenza-like illness, which is the data that we're trying to forecast. And so just a little bit more detail about the discrepancy terms. And here, basically, the discrepancy is the sum of two different terms. One is mu, which captures the week-specific discrepancy common to all flu seasons, and this is the one that captures the fact that week 14 is always higher than week 15. And then we have this delta that captures basically the week and flu season specific discrepancies. Every flu season and every week are going to be slightly different than what we've seen in the past, and so that's where we are able to capture this in our model. And so here, if you put everything kind of together, you have the future data, which is on the top, and that's what we're trying to forecast. And we have the SIR model in the middle, and then at the bottom we have the discrepancy terms. And so here, I'm going to show you a video of basically what happens. Every week we get more data, and then our model is able to be updated and adjust to the new data. And so you can kind of see how the 2017-2018 flu season played out. But you can see that at the beginning there was a lot of let me try to see if I can play it again. Okay. You can see that at the beginning of the season there was a lot of uncertainty in terms of where the number of cases were going to go, but as we get more data, then our model is able to basically kind of converge towards what's going to happen, and the uncertainty is reduced. And so, but there's one problem that I haven't really mentioned, and that is that I mentioned that the CDC releases data every Friday, and the data that they release turns out to be basically delayed. They don't provide real-time data. What they release on Friday is what happened the Friday before. And so we don't really know what happened during the last week, and so there's always a gap between today and the data that we're getting today, and especially since we're trying to forecast into the future, now we have to fill this gap and then also provide projections. And so this is a limitation with the way the data is provided, and the problem for why there is a lag between the data and the data in the models is because most of these data is actually collected from many different places, from labs, from pharmacies, from hospitals, medical records, and so all of them provided the information to the state, then the state provides the information to the CDC, and then the CDC kind of compiles all this information. And so there's a lot of there's a bureaucratic process basically in the collection of the data, and that's why whatever we're getting is at least 1 week delayed, sometimes it's 2 weeks delayed. And so in order for us to address this gap, we decided to start using social media. And so we have been exploring, Google Trends and Wikipedia searches and Google searches, and also Twitter to see what people are talking about. it turns out that people tend to now self-diagnose if they have a fever or if they have a cough. They try to self-diagnose and they go online and start searching for flu-like symptoms. And it turns out that this is actually it's more likely to happen when there are more cases of flu in a community than when they're not. And so just to kind of tell you how we're doing this, one of the many different data sources that we're using is Wikipedia searches. And so basically we've been using how people go on Wikipedia and they search for different articles. So if people are searching for flu or for COVID-19 or for dengue or for other diseases, then we're able to kind of take that information and then use that information to inform our model. And this is basically how it looks like. So here, the official data that is released by the Ministries of Health or the Health Department is shown in blue, and then our model is shown in red, and then all the Wikipedia the Wikipedia search articles are shown in gray. And so basically, what I'm showing here is that we take all the time series that are coming from Wikipedia, and then we take them into a model in order, and then we have just a simple regression model. And we've been able to find that internet search behavior actually correlates with disease incidence. So as the number of dengue cases increases, the number of people searching on Wikipedia or going on Google increases, and same for flu and tuberculosis in China. So the number of people searching online or talking about it online on Twitter is actually, it correlates with the actual number of cases. And so because of this type of information, we've been able to actually add a little bit more information to our model so that we're able to know in real time what's happening. Even though the data that we get from the CDC is delayed, so we can add one additional week. And so here, basically, I'm kind of showing the role of internet data. So here in the top, I just have a model without internet data, and so you can kind of see how there's a lot of uncertainty in our model, and also the forecast doesn't even capture what actually happened. Then in the bottom, we're adding some Wikipedia data, and you can see that the number of people searching on Wikipedia for flu decreased in the last 2 weeks, and so therefore we're able to add additional data to our models, and so we're able to better capture the spread of flu. And so that was basically what we've been doing for flu forecasting. And I'm going to skip I was also going to show you some of the things that we're using for dengue, but I think I'm just going to go to the our COVID forecast, and then I will wrap up. And so let me try to here. So I'm just going to jump to what we're doing for COVID-19 forecasting. But basically, we have been trying to apply this type of approach for dengue too, and now for COVID-19. And so I alluded to this at the beginning that we've been forecasting COVID for not just the United States at the state level, but we're also doing it globally. So for nearly 200 countries and territories, we provide forecasts twice a week, and then you can find the forecast here at the COVID-19-WSBA-gateway.org. And we have been making this forecast since early April. So and now it's been almost a full year of forecast. And so basically, the model that we develop is very similar to the flu model that I just described before. We have an SIR kind of type of model that describes how susceptible people are getting infected, and also how they move through the infectious, the infected class, and then they recover. But then we're adding an additional piece, which is a statistical piece, where we're trying to learn the growth rate and the case fatality rate based on the data that we are getting. So basically, we're collecting the case data from the Johns Hopkins University dashboard and the death data from the dashboard too. And so we're able to take the trends and then combine them with mechanistic or just mathematical models to forecast COVID-19. And one of the strengths of our models is the ability to adapt to situations we wasn't anticipating. As you know, COVID has been going up and down. There's a lot of behavior and public health orders that are playing a role in how COVID is spreading. But our model is able to kind of adapt and anticipate things that it hasn't seen before. The only problem is that our model can struggle with geographic areas, especially this was an issue at the beginning where there was little or no data when COVID first started spreading across the globe, especially since we wanted to do global forecasts. There were some countries with very few cases, and so our model wasn't really able to provide accurate forecasts. But once the numbers started to grow, then our model was able to do better. And so basically, we're providing short-term and long-term forecasts for cases and deaths. And you can see this if you check our website. And this is for the forecast for United States for March 28th. And so you can see we have here the cumulative number of cases that we are expecting in the next week and in the next 6 weeks. So basically, in conclusion, mathematical modeling has played a key role in helping us understand and respond to pandemics and outbreaks and many other infectious diseases. We are at the beginnings of epidemic forecasting. We have, as I mentioned, we're trying to borrow a lot of the tools and also the overall approach that the weather forecasting community has been using. And we're right now still kind of learning how we can make that translation. But I think that there's a lot of potential and there's a lot of opportunity for students and other researchers to make contributions to the epidemic forecasting community. We also have seen that there's a lot of value in adding different data streams. As you know, there's limitations with some of the data that we're using from the CDC or from ministries of health. And so by complementing our clinical surveillance data with other data streams such as social media or climate or mobility data, we can actually help make our models more accurate. Some of the challenges, obviously, for epidemic forecasting are data availability, especially when you want to do this globally. I think there's a lot of places where you can't find data that may be relevant for your model. For COVID-19, the emergent changes in behavior and also variants have also make it very challenging because you don't really know what people are going to be doing, and there are no databases actually capturing the human behavior. And so finally, I think the uncertainty piece is very important, as I mentioned, because we're adding different data streams in our models, and and if some of that data has uncertainty, then you're actually propagating that uncertainty into the model. So making sure that we are taking that into consideration is very important. And so finally, I just wanted to give a shout out to the whole team who's been supporting a lot of the different projects that we have on flu forecasting and COVID forecasting and dengue forecasting. And so here's some of the folks that are working on this. And I think that's all I have for today. And let me know if you have any questions.
Thank you, Sarah. This was great. Since we muted everyone, so I'll clap for everyone else.
I'm trying to see if I can share.
David, since I don't see the chat on MS Teams, can you see and tell us if there are any Any questions? David?
Yeah, there were no questions.
Oh. So if there are no questions, Sarah, do you want to go to that part of the presentation that you do, if you want to?
And so what part of the presentation?
Before COVID.
Oh, okay. Sure, I can talk about that. Okay, the dengue stuff. Just give me 1 second. So some of the, in addition to COVID and flu, we have been doing a lot of dengue forecasting for Brazil. And so for this project, we're also using a lot of different data streams, you know, clinical data, satellite imagery, climate, demographic data, Google search queries. And we're using different types of models. We have statistical models, which is what I'm going to be showing today. But we're also using mechanistic or system of differential equation models. And here I'm showing the different compartments that we're using to build these models. And for dengue, it gets a little bit more tricky because you have the mosquitoes and the humans interacting. So basically mosquitoes infect humans and humans infect mosquitoes. And so so here at in the bottom of the figure, you have the mosquitoes and then you have the humans. And so whenever there's interaction between humans and mosquitoes, then you get an infection. And this is a very similar approach to what we are doing for other diseases. And basically, we are exploiting a lot of different data streams. As I mentioned, satellite imagery. The reason why we're using satellite imagery is because ideally we would like to just know where the mosquitoes are and where the humans are. And if you know where mosquitoes and humans are, then you can basically estimate the probability of infection and exposure. However, mosquitoes, we don't really have a lot of mosquito information, especially for Brazil, just because it's such a large country, and so it would be almost impossible to track the mosquitoes across the whole country. And so in order to understand where mosquitoes may be, we're using satellite imagery to understand vegetation and water. So we're some of the assumptions that we're making are that if the vegetation is green, that means that there's probably precipitation, and if there was precipitation, then that means that there are mosquitoes, and mosquitoes are need water basically to survive and lay eggs. We're also using weather information, climate information, because mosquitoes have to live at a certain temperature. A lot of demographic information from the census. And demographic information is important because it allows us to differentiate between rural populations and urban populations. And also that we have information about inadequate sewage, for example, or poverty or garbage collection. And we know that the areas that probably don't have garbage collection will have more opportunities for mosquitoes to survive in those areas. And also we're using a lot of Google Health Trends data just to kind of track how people may be searching for dengue-related information or trends or symptoms or treatment. And so for this particular case, we are using different regression type models, statistical models, to help us forecast dengue in Brazil across different states and also different regions. And so here I'm just listing the 4 different models that we use. And so there are slight variations of regression type models for time series. And since we have time series for all the data that I mentioned before, and here I have basically the normalized error for all the different states and I know it's kind of hard to see the states, but basically the name of the 27 states across Brazil are listed at the bottom. And you can see, and although it's kind of hard also to see the numbers, basically if the color is lighter, it means that there's more error, and if the color is darker, it means that there's not a lot of error. So that means that the model is actually performing better. And you can see that some models do better for some states than for other states. And this was really important because normally we tend to just develop one model and then apply that model across all the different spatial regions or for the U.S. or across all the states. But this particular project made us realize that maybe we need different models for different states or for different regions, just because of the type of data, or some models seem to do better in some areas than others. And here I'm just showing you in more of a map format. We have the predicted, the predicted and the observed data basically, and so we trained the models from 2010 to 2014, and then we tested them from 2015 and 2016. And so this is basically what we saw during this is 2016, and then what was predicted. And overall our model seemed to be doing fairly well, but they struggle in some areas where we didn't have a lot of data, and we think that it's just because of lack of data or lack of infrastructure in those regions. But one thing that I wanted to mention here is that each of those municipalities on the top or states in the bottom are using a different model in order to basically forecast dengue. And one other thing that we did is also measure the contribution of the different data streams. Sometimes people think that the more data you throw into your model, the better the model is going to do. But we noticed here from this application that some regions, like the regions in gray or the states in gray, basically, they didn't need any additional data. Only with the clinical surveillance data, they were able to do fairly well. But some other states required the satellite imagery data, or some required Google data, and some required, a combination of data streams. And some states actually required all the data streams that we had. And so I think the take-home message here is that one size doesn't fit all, and so that kind of developing models that are more targeted for different regions, or that they use different data sources is probably the best solution. And I think that's all I had for this.
Thank you. Very interesting. Sure. And can I just follow up with the question of the last slide that you have with the team?
Sure.
So are those, so I'm assuming that COVID forecasting is ongoing projects for you, right? And the team that you showed, are those all employee in the national lab, or you have student internship that people are joining, going, and that will be helpful for our students as well?
Yeah, so we have, some of them are actually, some of them are students, some of them are postdocs. We also have probably half of them are staff members, so they're scientists, and then the other half are either postdocs or students. And so we do have summer internships. We have year-round also internships. If students are working on their PhD already, they already have finished all the coursework, and they want to come here and work for a year, one of their chapters for their PhD. They can come here, and then they can work with us and their advisor at the university, and then we can figure out a project that meets both our needs and their advisor needs, so that we can basically help mentor the student and hopefully allow him or her to get more chapters and publications in. So yeah, we have. So in fact, we get between 1,000 and 2,000 students throughout the year here in different forms, you know, from undergraduates, graduates, and master's degree and PhDs, and then lots of postdocs too.
Thank you, Sarah. If you can choose 2 skills that you're looking at undergraduates when you're hiring, what that 2 skills would be, the top ones?
So the top ones would be some knowledge of differential equations. I think it's very important, and in programming languages. So we use a lot of Python here or R. We also use MATLAB, but Python seems to be the programming language that we use for most of our models. Also, if they have some knowledge of statistics, I think that would be great too. But depending on the background, there are some undergraduate students that come here with more statistical background, and some come with more mathematical background. And so those are probably the courses or the skills that we look for.
Thank you, Sarah. David, any other questions?
No, that was great. Really appreciate it.
Well, thank you, Sarah. This was a wonderful talk, and we appreciate your time. Again, I want to sincerely apologize for all the technical difficulties that we have, but we are really glad that we managed to do the talk, and we enjoyed it. So thank you so much.
Yeah, thanks for the invitation. It was a pleasure to talk to you guys, and I'm sorry that we had to struggle with some technical difficulties, but I'm glad it all worked out at the end.
Thank you, Sarah.